Hi everyone, I'm Sargis, working at Webfontaine. So basically today during the upcoming 20-30 minutes I will speak about the common mistakes, not debugging, but common mistakes in Postgre. And actually my talk is inspired by this book. So most of content is coming from this book. So I choose the topics and adapt it, enhance it, and somehow modify it and choose what I think it will be nice to discuss and to talk. And yes, and to give you like baseline, so I'm software engineer, so I'm not DBA. So it will be somehow, uh, yeah, not very deep dive in DBA administration tasks and backup or organizing a replication. So it's more like different perspective basically. So before starting, I would like to there is a notion like a mechanical sympathy. It's common notion. It's not related to the database itself. So basically, it's when you use a tool or system with understanding of how it operates the best. And as a software engineer, so to understand Postgre or any database or any subsystem in better way, if you understand it well, so it helps to, in case of Postgre, to write better application with better performance, to provide better application design, and use Postgre good parts, etc. So it's very important, like for everyone to understand like your tools or your platforms. Uh, yeah, also it helps like you to collaborate with DBAs more in more close manner. Basically, it's before escalating things to your DBAs. So basically, you can solve many things yourself, to troubleshoot yourself, to use some explain, analyze, etc. To solve your problem yourself, and also helps to discuss with DBAs using the same language, like optimization, index, I don't know, hash join or things like that. Uh, Also, in general, for me, it's like if you are if you are learning a big system like Postgre or something like, so you are learning a lot by its internal design, by how it works, like, and it's useful. It's very useful knowledge, like as a software engineer, like it's not for every day, but usually it's like it has a very good impact on me, and I think for everyone is good. And let's start the actual topic. So the first one is actually it's related to the charts, and we will cover why text is always better choice when using char. What is char? So it's things like blank padded textual data type, and it always store exactly n character, which is very important. So if we give the example, let's say if you like this Postgre word, it has 8 characters. So if you define as a char 10, so it will be padded by 2 white spaces, and it will store it with width by white spaces to the database. Basically, it will consume more disk space. So one problem with char also is like it's very inconsistent for comparisons how it works. For equality, it's ignoring white spaces. So as you can see, like it's ignoring white spaces here. But if you try to use char for like because there is a white spaces. If you try to use with like and regex, so it will not match because internally it's using white spaces. So it's kind of problematic for this. Uh, yeah, other things is like is if you cast like to the chart and it's truncating data, which is coming by the way for SQL standard, but it's kind of can be without any error. So it can be you can lose some data without noticing. And as I said, one big problem with char is storage inefficiency because it's saving this blank padding into the disk, so it's consuming disk for nothing. And also it has some performance impact because wasting some CPU cycles by adding or stripping these white spaces during the operation for certain operations. It's not for always, but There is a such kind of degradation also in general. So in general, like use text, it's no padding, it's unlimited length instead of char use text. So we will cover of course varchar also because it's related. But in general, it's like use text because there is no padding, unlimited length, better performance, and better compatibility for drivers, connectors, etc. Other type is varchar, which is so it's somehow similar to char, but of course it's variable length and it's not doing any padding. So yeah, it's not doing any padding and only stores the character we provided. Again, it's like truncating the data, which is SQL standard again. And it's not the limitation itself, but it can create some problem. Let's say if we yeah, this one is just a minute. Yeah, let's say if we create a company table with company name with varchar 50, and if we insert with less character, of course it will accept. If we insert with more character, we will get fail, which is fine. But let's say we want to extend now we want to add more character in our tables. So if we have very big table, so we need to let me go back. So we need to alter our table, which in case of very big table, so it will require some table lock and it can cause some downtime. Like there is a varchar myth. So in general, so there is no any performance benefits over the text. Storage and performance are identical to text, and only difference is like length check. But in text we can have check also. So we can define constraint like check and like this. It can be a little bit probably unusual, but we can have explicit error messages and easy to modify or removing constraint later without long logs. And the better approach for me is to define create domain. So in this example, so you can define create domain some short text and some constraints. So basically, it's like you're defining your custom data type, and after you can use this data type or type for other like here. And as a benefits, you will get reusable and centralized logic built on the robust text type. So it's easier to change. You have centralized and reused, let's say, data types, etc. So in general, it's more robust design, I think. Yeah, other topic is to cover is how a simple function call can destroy the query performance. In general, like applying function or expression to the index column in our var, so it can kill query planner. So basically, it will not use index, so it will go to the sequential scan. And in the end, we will have like keeping this index for nothing, just it will slow our write and consuming these spaces. Here's example. So we have, let's say, some table and with indexing on this. So here it will do index scan. But if you want, let's say, to truncate and compare, so it will go to the sequential scan because it's using some function over our indexed column. So it will basically will not use index, so it will go for the sequential scan. As a solution, one way is to move this customization to the right side of the code. It's like here is like changing to the kind of range syntax, which can be somehow ugly. And probably easier, more clear solution is to define expression index like this. Like if you know we are going to use this dead trunk for querying a lot. So basically we can define such kind of index and it will use still index in this case, but query must match the index expression exactly. Other things is related to the index is to choose correct index type for our tables or for our design, and the default is the B3 by the way. So B3 is good for equality, range check is like equals, greater, between, etc. It's order by and prefix based like searches like here. But it has some problem for other search cases. Like in this case, it's using substring search, and B3 index cannot be used in this case. So here, I mean, this one we can consider it as an expression index on this, but in this case, it have to go to the disk to read or disk or buffer, etc. Doesn't matter in this case, but it have to read additionally for amount and invoice date. But if we add index like hovering index will include, by the way, it's not mandatory to use this one. We can move this to this part also if we go. But of course, yeah, in this case, like we are creating index like this. So on this column and are asking Postgres, please include these two values into the index. So when we are querying this one, it's hitting, let's say, this customer ID and returning this value directly from index. So without doing additional I/O. Yeah, to find basic indexes, it's you need to use explain analyze. So one way to do it is use explain or explain analyze. So if you see sequential scan for large tables, so it's better to consider or to review your queries and to add index. By the way, for small tables, even if you add index, it can still possible that optimizers choosing sequential scan instead of using index because it's deciding or considering to use sequential scan for small tables is more efficient instead of using index. That's why the large table here is important. Also, like if you see that index scan followed by a large number of hit pages in your analyze, so basically it's a good opportunity for consider to use covering index. Yeah, so over-indexing is just based as under-indexing. Yeah, while missing indexes make read slow, so unused indexes make write slow. So for every insert, update, and delete operation, it should update, like do maintenance for the indexes. And there is no, of course, there is no any benefits to have unused indexes in general, of course. And yeah, there is a query how to find it. And there is a note like static resets on the server restart. It's not the query statistics, it's the statistics of the index stuff. And other things to consider is the duplicate indexes problem. Like if you start to create indexes without naming, like this, so Postgre will generate some names for it, and basically we'll have two identical indexes for nothing. And that's why it's always good to use name for your indexes, or use if not exist, also use if not exist. Even like we said, okay, we need to remove the unused indexes, but in some cases, if you remove unused indexes, we can have trouble. And the scenario is like, let's say if we run our index audit with the previous query, find out some unused indexes in primary database, and we drop the unused index, and after let's say 3-4 hours, we got call from analytics teams that there are reports on read replica. So please, like there's a primary database replica, it's taking hours instead of minutes. So root cause basically, when we are removing indexes from primary DB in case of physical replication, which is important for physical replication. So it will remove the index and read replica also. So basically, like even if this index is not used in your primary database because it's not for analytical role, it will remove from the read replica, and it can create a big problem for analytical reports. We'll speak about the connections. So there is a myth again, like more database connection will lead to better application performance. This table is from book. So as an example, I think he did some benchmarking, etc. As we can see, so after a certain point, so it's starting degrades. I mean, his latency and transaction count is becoming lower. There is a degradation in the numbers, and with 2,000 connections, so it's quite bad situation. So why it's creating problem? Basically, for Postgre, each connection is processed per connection. So if you have too many connections, too many operating system processes, and operating system need to handle with this. So there's a context switching things, which is very expensive for operating system. So it is becoming slower. So there is a lot of processing for operating system. Memory pressure. So each connection is a each connection is consuming memory as a process. Each connection consumes memory. So if you have a lot of connection, of course, it will influence server RAM. So it can lead to the swapping, which is of course very bad for operating system itself. And with a lot of connections, Postgre have to keep some lightweight logs for internal data structure, which is creating some kind of log, completing for the log. So which is in general, if you have a lot of log competition, regardless it's Java or any language, or doesn't matter language, any application is not good for the performance. And the solution is connection pooling. In this example, just example of course, like we have in the middle DG bouncer, which is connection pool solution. And we have a lot of connection coming for client, but DG bouncer is left keeping only 50 connection to the database. So it helps to reduce load to the database and somehow protect database to be overwhelmed. In general, like more connection is not always better performance. So yeah. Also, other interesting things for me is like the cost of the idle connections. So it's not like idle connections are free. It's very connected to the every open connection active or idle and overleads to the start to start the transaction in Postgre because it's kind of this MVCC architecture. So what is MVCC means? In general, before starting new transaction, Postgre somehow creating snapshot. It makes all read without need any login, etc. But Postgre to be able to create this snapshot, you need to check all states for every open connection. So basically, if you consider like snapshot creation cost, its complexity of the total connections. And yeah, if you have a lot of idle connections, even we are not doing nothing, it's slow down in things. Most cases such problem is coming from misconfiguration in application side, like pools and etc. Like in this, I think it's Ikari pool, but it's like there is idle timeout 0, so it never timeout. So if you have 5 microservices like this with 5,000 connections, so it will have 5,000 per idle connection, so it will be a problem for us. So one solution is using PG pool with transaction mode. So basically, when the application starting transaction, it's kind of renting this connection to the application, and once it's committed to the rollback, so it's returned to the pool. Other things is configure better our application's pools by setting idle timeout to automatically close idle connections. And from Postgre 14, there is an option for idle session timeouts, but the applications should be designed to handle unexpected connection drops in this case, because Postgre itself will cause connection, so probably you need to retry your pool, need to configure to retry things like that. Finding the problem is to find idle connection given to query. So, by the way, I will share the slides later on, so probably you can be useful. Other things is to use partitioning for the large tables. So if we have very big table with many, let's say, rows, usually even the simple count, select, and set is very slow, even the delete is very slow. And one way to do it is there is declarative partitioning in Postgre. So as an example, here there is a table definition, basically defining partition by range is times time column. And after we are creating child tables, this name is just for not important, but just to easy find out things. And after is pointing to the partition of to the list table and defining the range. So if you are querying the main table, it automatically choosing correct partition. So basically, no need to scan full table for the searching, etc. It also helps for the maintenance, like the drop delete is becoming very fast. There's a tool like Digipartman. So it's good for time-based partitions. So it can automatically create new partitions for future data, automatically detach or drop all partition based on the rotation policy. I'll speak about the improper memory allocation. And so in general, let's say we can split Postgre memory into main areas. One is the shared buffers, which is basically database page caches. And other one is local memory, it's per connection, it's both mostly for sorting, caching, and other query operations. I will speak about the query operations. And maintenance workmem, which is for vacuum, creating this concept. So it's very critical to understand how workmem configuration parameter works. So basically, to compute potential memory usage, so it's max connections, work memory, and operations per query. If it's set too high, so it can easily demand more memory than we have. So we will have the same issue like swapping and other things. And to cover what I mean by, or what we mean by operations, the query operations. So let's say we have such kind of complex query, and we have here 6 operations, like 2 joins, aggregation by group by, sorting for distinct operation, and final sorting. So basically for this query we have 6 operations. So basically potential memory, potential is not required, but potential memory can be 6 times work memory. So in scenario like this, like max connection, work memory like 256 and complex query average operations, it's 4 operations per complex query. So we can have such kind of numbers, and even if we consider like only 50% using complex queries, it's still quite big. And yeah, if you have like if our Linux processes, in this case Postgre, is consuming too much memory, Linux or OM killer will terminate the most consuming memory consuming processes. And in this case, if it's Postgre, so it will kill Postgre backend process, and Postmaster process will detect like there is a issue with his processes. Basically, it will assume like there is a probably shared memory corruption, and it will terminate all other database connections. So basically, it will do like kind of full crash recovery mode. So a single OM kill can bring down the entire database. In this case, because of this configuration in work memory and etc. Yeah, best practices is to start some depends on your experience or your workload, etc. To choose some like 4 megabyte. It's important to monitor temp files, because if you have a lot of temp files, it means like you can consider increased work memory, because usually temp files created when you are doing query and there is not enough memory. There is not enough in work memory, basically, to be able to kind of sort or to do things like this. Postgre starting to use disk for such cases, so basically creating temporary files. So it means there is not enough memory starting to use disk, which is slow and which can slow down your queries. Use connection pooling, which is also, this one is nice to consider, because if for certain queries you are considering you need more work memory, basically you can set it per session. And you can, it's nice to consider this one for better functionalities. And there is a kind of low, like 20, for shared buffer for 25% of RAM should be given to the shared buffers, but which is outdated, oversimplified, of course, like all numbers. Usually, like for OLTP routes, so we are giving shared buffers much more, and for OLAP cases, we are giving less, because usually for OLAP, it's doing large sequential scans, and we need to, it's better to leave more memory for workmem or OS file caches. Let's speak about UIDs. I think it's used a lot. So it can be tentative to use UIDs because it's globally unique. It's somehow secure because they are not sequential, so you cannot get the next ID. Instead of this one, you will have this one. And it's distributed friendly because, like, for multi-node databases, like, it's globally unique. But it's coming with significant cost, and mostly it's related. One part is the size, so it's quite big as digging. And if you have, let's say, big table, let's say with big int or UID here, it's like inserting 100 million rows using big int as a the serial numbers and as a round on this one. So the difference will be here. So basically insert and create will be much faster in big int. Also the index with UID, it's 40% larger compared to the index on big int. And primary reason is why it's slow, and it's not only the state but also it's slow, because in case of big int, so we are adding new rows in sequential way, so it's very friendly for index data structure for battery, let's say. In case of random UID, so it's because it's random, so it's force Postgre to constantly split index pages or rebalance battery, etc., which is slow and time intensive. And I think from Postgre 18, the UID version 7 is coming, which is chronologically sorted, and it's not eliminated, but it's almost eliminated entirely, like in this fragmentation program. But I think the size will be the same.
Second speaker, Momjian, welcome back.
About the mistakes you made, but if you know Jimmy, he sort of likes to see the negative things. I don't know why. So it totally made perfect sense. Yeah, it is wonderful to be with you. I was with you, I believe, in December. Is that right, Emma?
Yes.
Yeah. It is. My name is Bruce Momjian. I am from the United States in Philadelphia. I have been working with Postgres for 29 years. I am one of the co-founders and one of the core team members. It's amazing to see so many people here. Super exciting, also super strange, because I remember the first time, I've worked with open source since the early 90s, and I remember the first time I went to church and somebody knew what I did. And you're like, because what I do is so strange that almost nobody knows what I do. Most of the people at church think that I either sell drugs or I'm a spy, right? That's pretty much what it is, because I travel so much and I go to strange places and I come back and I don't appear to have a normal job. I just sort of around. And then I went to another church and I had two people who knew what I did. I thought that was very strange. So now I'm in Armenia and you all people know what I do, and that's also very strange. So it's basically when your work life, your work life and your basically heritage kind of merge together. It's a very unusual experience and super exciting. I was here in, I believe, 2005, trying to build up the software industry here in Armenia, because obviously we're a landlocked country. We don't have easy import and export, but there's a huge amount of intellectual talent here. And in 2005, actually the United States State Department, USAID, sent me to help build up the software industry here. I came with a group of people who were doing that, and they continued the work. I didn't come back for a large number of years, and now obviously the software industry is doing very well in Armenia, and we want to continue that trend. And obviously for the Postgres world to get bigger is obviously super, super exciting. So yeah, I could not be more excited. I am in the United States, I am in Armenia actually for a medical mission trip. That's the reason I originally came. My wife, Christine, is over there. You want to stand up there, babe? There you go. There's my wife, Christine. She came a week before me to work to create a clinic in Sicyon. How many people have been to Sicyon? Anybody? Oh, okay. I love that town. So she came a week early. Spent a week doing a medical clinic there. I was actually in Switzerland doing a conference and a couple of customer meetings, so I couldn't go to Sicyon, unfortunately. But then the last week we were in Gyumri and Vanadzor, doing a medical mission team there. I think total number of patients is 850, something like that. Again, a lot of these small towns don't have normal. They have medical care for people who have a lot of money, not a whole lot of medical care for people who don't. So that's why people from the United States have come to create these clinics. We do the standard things. I don't know anything about medicine at all, but I know how to sort of do lab, and I know how to sort of help people and steer them around. So that's exactly what I did. And then this coming week, we're going to be in Baird. Anybody know where Baird is? Yeah, okay, right. So we're on the northeastern part of Armenia. We'll be helping a soup kitchen there, and then we're going to Hankovan, a youth camp called Shorik. Is that right? What? Sholik, yes. And we'll be doing a camp there, and then from there I'm going to Hong Kong. So with a lot of excitement, I'm going to be going around there. I'm going to visit some customers. I'll be speaking Shenzhen, that is in China. Then I'm going home, and then the rest of the year is like Mexico, Brazil, UK, Netherlands, Riga, Latvia. We have a big conference coming up in October. I'm going to Raleigh and probably Japan. And anyway, this is my website right here. The slides you're going to see today are actually on that website. So anytime you want to see this set of slides or a video, there's actually 63 slide decks on that website. That QR code should take you there. 2,800 slides, 130 videos of me delivering talks about Postgres. I love this topic. I actually got involved with Postgres because of the optimizer, and I'll explain why as we go through it. But I've always been the kind of person who I was never happy with, normally when you get a piece of software, somebody says, okay, here's how you interact with it. Here's how you send commands. Here's how you write a program. Here's how you drag and drop things. I was always trying to understand, how does it work underneath? How does it work all the way down? And actually, the optimizer is the thing that got me involved with Postgres. In the 1990s, I was an application developer. So I was writing applications using a relational database. Many of you are doing that now. And at that time, I was using Informix and Ingress. And I really was curious, how does SQL work? I send something that looks like an English sentence, which is SQL. How does it figure out how to get the answer? Like there isn't a person in there. Like, how does it do it? And then even deeper than that, as Sargis mentioned, there's indexes it has to choose. There's different things it can do. How does it figure that out? How does it do it? Well, the databases I used were closed source. Postgres was open source. I could actually look inside of Postgres and I could see exactly how Postgres operated. And that was exciting. So I got involved with Postgres because I could look inside a relational system and see how it worked. I could see how the optimizer worked. I could see how it figured it out. And that's exactly what I'm going to talk to you about today. We'll take some questions. I actually have 2 slide decks. We'll take a little break in the middle. But again, it should be really, really good. Any questions before we get started about anything kind of in general? Okay, it is really great to be able to talk to you. Again, when I was an application developer, this was me, right? I was in this orange box writing application code. And I always kind of was wondering, well, what happens over here? Like, this is like a mystery to me. And I don't like mysteries. I like to figure it out, take stuff apart, see how it works. And actually, I would recommend that to you. A lot of times when I would be in meetings, all the engineers who focused on just their piece of the puzzle couldn't really debug anything that happened unusual. So a lot of times I'd be in a meeting and they'd say, this thing's slow, or this thing isn't working, and I'd say, oh, it's probably the I/O subsystem, or it's probably this kernel part, or it's an interaction between these other 2 things. First couple times, people would just ignore me. Like, they would be like, this guy is new, he has no idea what he's saying, we're just gonna keep talking, like he said nothing. Happens to me sometimes, right? I say something, people are like, oh, I don't understand why he's saying that, he must be a weird guy. But then, after a while, when they figured out what the cause was, it ended up matching what I said in the meeting. So like the 4th or 5th time when I'd say something, they'd be like, well, why do you say that? And I said, well, it's because these other things, you're running out of RAM in this area, or this kernel thing is happening, or your I/O stack is set up this way, and the random I/O is killing it. And they'd be like, well, why do you know that? And I'm like, well, because I studied the compiler design, I studied the operating system, I understood how the CPU works, how the cache on the CPU works, how basically the instruction set works, and the I/O subsystem, and then I could understand. So for those of you who are really curious, don't feel you have to stay stuck in your little box. And actually, the fact that I didn't want to stay stuck in my box is why I'm here today, right? Because I'm the type of person who kind of takes stuff apart, tries weird things, and tries to figure out exactly what's happening. And it's actually served me well. It's a lot of work. There's a lot of times my wife would complain, why are you in the basement? My office was in the basement, so why are you spending so much time in the basement? Because I was researching something I didn't understand. And I would explain that to her and say, okay, but do you need to know that? And I'm like, well, not really, but I just really want to know. I'm curious. So again, for those of you who are wanting to have long careers, there's very few people my age who are still doing engineering. And I think it's because some of that curiosity has sort of stayed with me. So again, what we're going to talk about is not the application code, okay, not even the design, but what happens inside of here. So this is a flow chart of Postgres itself. There's a lot I could talk about here. And we're going to focus on this area right here. There actually is a whole bunch of stuff right here. For example, here's an internals presentation I wrote, and you can basically if you download these slides, anything in blue you can just click on, and it'll take you to that section of my website. Download the slides, or take you to a blog that explains more about it. I'll show you some more blue, but again, don't forget to type any of this out. You just click on download the PDF and click on the blue, and it'll take you to those things. So we're going to look at this box right here. We're going to blow it up. When I started with Postgres, I would say studying this process took a huge amount of my time. And I'll admit that I did this while I was fully employed. So when I was fully employed in the mid-90s, I was paid by the hour. So every hour I was playing with Postgres and learning, I wasn't getting paid. A lot of people wouldn't do that. A lot of people would say that's not fair to your family. A lot of people say you're losing a lot of money. But my career, I would say when I started with Postgres in the 90s, was kind of just doing the same thing over and over again. I was writing financial reports for law firms. That sounds, what could sound more boring? I was writing some applications for law firms. So my engineering growth had really stopped, right? I mean, 7 years of the same thing, you're not really learning anything new. And you're just kind of turning the crank. Your customers are happy, you're producing good output, but you're not becoming a better engineer. You're not learning new things. So when I got started with Postgres, again, on my free time, and I was actually worked in my free time for 3 or 4 years until I was fully employed with Postgres. You would study this process, right? I mean, this is hundreds of thousands of lines of C code. If those of you are familiar with any C coders here? Oh no. Oh.
Not for every day.
Okay, I'll recover. But yeah, you're reading hundreds of thousands of lines of C code. And in fact, one of the things that I learned, I was a really good. When I was working in the law firms, I was really good. Like I would walk into a law firm, and everyone would be excited. They're like, "Oh, Momjian's here." Or I was called bow tie because I wore a bow tie. No bow tie today. It's July. It's just too hot. But I'd walk in, they'd be excited because I would probably be able to fix whatever problems they had because I studied that whole stack of their software. But when I started working in Postgres, I was working with people all over the world and incredibly smart people. So very early on, I realized I'm good, but I'm nowhere near the class of these people. These people are so smart that I'm better off helping them to improve Postgres than improving Postgres myself. So I mean, I couldn't be the kind of guy who said, I'm just going to do everything myself. But in fact, I learned early on that enabling others to do stuff was actually more effective. So I wrote this presentation very early on in my but it's been updated. But I wrote it very early on. There's in fact a flow chart. If you go to the Postgres website, you can sort of dig down. You can actually find a flow chart. You can click on each of these little blue boxes, and it'll take you to the source code of how the thing works, right? So anyway, really kind of crazy, but again, that sort of box is what got me kind of going. Would my wife like to add anything since you're here? Maybe I misrepresented something.
No, it's good. It's good. We had young children those years where he was working by the billables and then all the free time playing with Postgres. Yes.
It's not. It's when you have a vision of what you want to do, it's really hard to explain. Sometimes even to your spouse, like, why am I doing this? And you don't know why you're doing it. That's the weird thing. Like, if I had an explanation, she probably would have accepted it, but I didn't. I just sort of felt this is what I wanted. I guess, this is what I wanted to do. This is what I wanted to do to grow my career and learn more about engineering. I never took a computer computer science class in my life, okay? I read really thick books about computer science. And in fact, it was so much that my wife said, well, you should get a doctorate because you're reading the same books that you read for a doctorate anyway. And I said, you know, not that I don't like school, but I'm better off reading the books and then trying stuff myself at my own pace than sort of sitting in a classroom. So again, that was sort of why I ended up studying this thing. In fact, if you're curious about it, I have this URL right here from this company in Japan. I'm sorry, in China. They do a really good job of explaining this entire process. So basically, the query comes in and it gets split into words. So you know how we have words, like you have a sentence, an SQL query, and it's basically a set of words, right? And if you have a string, that's a word too, or a token we call it, okay? And it breaks it down into a set of words, and then down here, we handle things like insert, update, delete, and we handle views. And down here, this is what we're going to talk about today. This is the optimizer. And then finally, it gets sent to the executor. And this is really, to me, this is the brain. That optimizer is the brain of the system. And it was a real black box to us. At that point, when I started in 1996, Postgres had already been around for 10 years. So when I started, I'm saying I've been around for 29 years. Postgres has been around for 39 years. It goes back to 1986. Does anyone have parents born after 1986? I'm a little scared to ask. No, I guess I'm safe there. But effectively, this software is 39 years old. And what's really crazy is it's still relevant to the point where almost every relational system except Postgres is fading, right? Oracle fading, Microsoft fading, IBM DB2. In fact, all three of those support Postgres. There's an Oracle Postgres in the Oracle Cloud. Microsoft's a huge supporter of Postgres. IBM is a huge supporter of Postgres. So again, it's kind of weird for 39-year-old software, normally which would have been fading at this point, or would have faded long ago, to not only be relevant, but to be the cutting edge of relation systems today. Really, very, very strange. I do have a talk on my website about open source and the open source life cycle. It's called Will Postgres Live Forever? Because you're almost here, you're 39 years old. So again, if you're curious about that topic, feel free to download the slides or watch the video. Okay, so let's get started. What does the optimizer do? It has to make three choices. And Sargis mentioned it a little bit when he talked. One is called scan method, one's called join method, and one's called join order. These may mean nothing to you right now, but as we go through, I'll have diagrams and show you exactly what these things mean. Again, another different, excellent blog entry from a Chinese company about the optimizer. This one also really, really good in explaining how the system works. You might be kind of surprised I'm mentioning blog entries, but again, when I'm thinking, how do I get people excited about Postgres, I'm thinking, how do I teach them? How do I train them? How do I get them excited about what we're doing? And the software is so complicated that somebody coming in and saying, no, don't just look at the C code. Here's a blog entry that kind of lays it out for you, gives an understanding of how all the pieces fit together, so then when you start getting involved, you understand it. That's, again, another reason that when I see a high-quality blog related to one of my slides, it goes one of my slides. My slides have tons of these things, to the point where sometimes I go to a conference, somebody will pull me aside and say, I went to your website, I spent 3 days there. I'm like, is that good? I'm like, yeah, it was good. I watched all your videos. I clicked on a lot of these links, I read those blogs. I just kept going because there is so much excitement about what we do. At least to me, anyway. And I think it's sort of continuing here. Okay, so first let's look at scan method. There's three types of scan methods. There's something called sequential scan, a bitmap scan, and an index scan. But before we talk about that, we're going to set up a little test environment. Okay. So what I'm going to do is I'm going to query one of the system tables. Actually, it's called PG class. And PG class contains the name of all of the tables, of the system tables in Postgres. the first letter. I want to cut everything but the first letter out of the system table names, okay? And I'm going to create a temporary table that's going to have the first letter and then a whole bunch of X's, just so the row is not like short, it's kind of a normal length, okay? So we have a single letter, and then another column, which is 250 spaces, X's, I'm sorry, and I'm going to put an index on that, okay? Now, the rest of these slides that you're going to see is actually that SQL file right there. So if you later want to run what you're seeing today, you just download that SQL right there, you run it through PSQL, just fly on your screen, you'll see exactly what. You'll see the exact same thing you're seeing in the slides, without the color, without the headings, just kind of workable. And that's the way I wrote the presentation. I wrote the SQL and then copied it in. Okay. So another idea, the helper function, we're going to call it lookup letter. And that is basically going to give us a distribution of what's in our table. So in our table, 83% of my rows are the letter P. That sounds super boring, but again, once we get started, you're going to figure it out. 3% are C, 2%, 3% are R. Down here, the K and the I, there's only one of those. There's only one K and one I, okay? Again, there's kind of a distribution of the system tables in Postgres, okay? So, let's look at the optimizer. Sargis already mentioned the word explain. The explain allows us to look inside the optimizer and say, here's a query, tell me what the optimizer wants to do with it. It doesn't execute the query, it just tells me if it was to be executed, what is it going to do? And when I do the most common value here, a P, we get something called a bitmap heap scan. Right? Let's not worry about what that is right now. But what's weird is that we remember the P was the most common value. Remember, this is the brains of Postgres. And when we do the most common value, we get this bitmap heap scan. But when we use a less common value, the D, we get a bitmap heap scan. And when we use an I, we also get a bitmap heap scan. And the thing that this tells me is Postgres isn't very smart, because it has done nothing smart with effectively the most common value and the least common value. And the reason for that is because there are no analyzed statistics. I'm not sure how many of you have heard of analyzed statistics before? Okay. There's no analyzed statistics in the system. So what I'm going to do is I'm going to run a command called analyze. And as soon as I do, a P becomes a sequential scan, which is what we really expect. Now, some of the reason you don't know about these statistics is because in almost every case, Postgres has an auto vacuum process, which will automatically create these statistics for you without you having to do anything. It runs every minute. It looks for tables that have new rows in them. It looks for tables that have changed. It'll automatically generate fresh analyzed statistics every time it needs it. However, you might remember back here, this is a temporary table. So Analyze can't see temporary tables, okay? This is probably another mistake, right, that the book could have mentioned. So anytime you're creating temporary tables, it's your responsibility to create optimizers statistics on it. Because auto vacuum, remember temporary tables are private to the session, so the auto vacuum just can't see them. And as soon as I do that, I get a P, and what happens in B, we do a sequential scan, we just read through the whole table. Now this is very efficient. Remember I talked about the I/O system, most I/O subsystems will automatically preload pages as you're doing the sequential scan. It knows, hey, you keep reading from the same table in a sequential manner, I'm going to prefetch those rows from you from storage so you're not having to wait for them. This is a good example, I think, of knowing your storage subsystem to understand how it behaves when you're trying to debug a problem. Okay. So this is incredibly efficient. When I do a D, I get something called a bitmap heap scan, and what that does, it effectively goes to an index, and it creates a bitmap of all the matching rows, and then from that bitmap, it actually goes to the heap to find the actual rows that goes with it. Okay. And when I do an I, which is the least common value, I go a direct index scan. This is actually a B-tree index. Sargis mentioned that. So we have the key, we have our key, and we just takes me directly to the row that I'm interested in. Okay. So that's a good example. Remember, when we didn't have, I'm sorry, back up. I'm sorry. When we didn't have these analyzed statistics, we were getting the same thing. Now, as soon as we added them, it knows when to do a sequential scan, it knows when to do a bitmap heap scan, and it knows where to do an index only scan. Any questions? Okay, great. Okay. Okay. Yeah. That's what we, okay. So, what I'm going to do is I'm going to show you kind of a query that tries all of the values automatically. There's a little sort of SQL magic. I'm using common table expressions, so I was about to talk about that, where it kind of goes out, it finds all the letters, and it kind of runs them like this. And this is what I really wanted to show you, okay? You can see the most common value automatically generates a sequential scan. All of the values from the most common all the way to the least common generate a bitmap heap scan. And then as soon as we get to the rare values with only one, it automatically jumps to a sequential scan, an index scan. So the point is that you don't need to know anything about your data. You don't need to know how common the values are. You send the SQL to the server. The SQL automatically gets optimized, and the system, using those statistics, which are automatically refreshed, is able to figure out the best way to give you your results. This is part of that brain of the system, or the smarts, that I was trying to understand how does it work, how does it do that, and this is actually that. Okay. Now, you can actually turn off sequential scan and bitmap scan. You can force the system to use an index scan, but what happens is what was 21 becomes 56. So effectively, it becomes very expensive to do an index-only scan on all of those rows. Okay. So I don't recommend you do that, but if you wanted to test it, you could actually force it to use a different, scan method. Then you can time it and decide whether the optimizer is actually helping you or not. Right? Kind of interesting. Okay, any questions about that? Okay, so let's go to the next thing. The next thing is join method. We have 4 ways of joining tables. Remember, relational systems are fundamentally joining different tables together, different combinations, different where clauses, all these things that you can do. There's 4 ways they can be joined. 2 are nested loop, 1 with an inner sequential scan, and 1 with an inner index scan. 1's a hash join, and 1's a merge join. I'm going to show you all 4 of those as we go through with diagrams and with pseudocode to help you understand what it's doing. So we're going to need 2 tables to do that. Obviously, we're going to join 2 tables. We need 2 tables created. So we're going to use some rows from pgproc, and we're going to load those into sample1, and we're going to take some other rows from pgclass, and we're going to load those into sample2. Now, we're going to start out with no indexes and no statistics, and then over time, we're going to add those and see how the results change. Okay, so here is pretty simple join, sample 1 to sample 2, with a where clause that selects only 1 row from sample 1. So, pretty easy to understand. It does a nested loop. On sample 1, it finds the value is 33, and then it joins that to sample 2. This is what a nested loop looks like with an inner sequential scan. You're basically joining every row to every other row. Now, the reason this happens is because we only wanted 1 row from this side, so it's pretty efficient, right? But as you're going to see later, once we start to request more rows from that outer side, we're going to start to get different plans because those can become incredibly expensive. Imagine if this is 1,000,000 rows and this is 1,000,000 rows, and you have to compare each row to each other row, that's 1 trillion comparisons. So you can see how there's sort of an explosion of cost in this nested loop example. Okay, so you only do it actually for very small tables, so again, when they get big, something different happens. And this is what the pseudocode for that looks like. If we ask for all the rows over 33, we get something called a hash join. And in a hash join, we take the inner side and we basically create a hash in memory, okay? So we can do really fast lookups. Because remember before, we were having to scan the whole inner side for every row. If we process the inner row and we put it in memory, we can like hash and look up stuff real fast. So for this row, we can hash, we know it's somewhere in this set of hash bucket. For this row, we know it's somewhere in this hash bucket. And again, that greatly speeds up what we're doing. And again, another great log entry here about hash joins, hash aggregates. Okay, and that's what the pseudocode for that looks for. Now, if we do the join with no where clause at all, okay, then we effectively get something called a merge join. Now you can imagine this is that really big table joined with a really big table. And what happens here is we sort the outer side and we sort the inner side and we compare kind of lockstep. So we say, does this match yes? Does this match no? Okay, now we can move down to the next row. Does this match yes? Does this match yes? Does this match no? Okay, now we can do that. And the reason we can do this is because we never have to go backward, right? We know that if this doesn't match, there are no rows earlier that could match because it's all sorted, right? So we can just look forward and sort of just lockstep go through. And again, for really big tables, this is the only efficient way we can do it. Nested loop would be a disaster, too big to fit in hash join in memory for hash join, okay? So for the really large tables, this allows us to do, a really big join, okay? And that's what the pseudocode for that looks like. Another case here, for example, if I join sample 2 to sample 1, I just switch the order I specify, means nothing to Postgres. Postgres is what we call cost-based optimizer. It's going to do the same thing no matter which order you specify. Okay. Now, we've talked about that. I remember I had no indexes, no statistics. Let's add some statistics. And let's see how that changes. So we add statistics to both tables. Now, when I do what was a merge join becomes a hash join. Because it now has a better estimate to say, table 2 will fit in memory. It didn't know that before, it didn't have statistics, so it fell back to a merge join. Now that it knows it will fit in memory, it's going to do a hash join. That's exactly what it does. I can even do a right outer join, and I can do what's called a right hash join. It's kind of unusual, but we have a special hash join just for outer joins. Sometimes some relational systems can't do that. Postgres can. If you've ever seen a cross join, this is actually legal SQL by the SQL standard. What a cross join is, effectively join every row to every other row. Well, that one you have to do a merge, a nested loop, right? Because they're effectively telling it, I want everything joined to everything else. Now we're going to add some indexes, okay? And this is going to add new opportunities for us. So this is the first query we had, sample equal 33. Now we're doing a nested loop, but instead of doing a sequential scan now on the inner side, we can do an index scan. So remember all that one with all the arrows pointing to everything? Now we're like, oh, where is that row? Oh, that's right there. I don't have to scan the inner side anymore. I can go right for the row. Okay, same thing with this one. Oh, that's right there. I don't have to go and check somewhere. So again, with an index, remember Sargis was talking about index, not only is the index useful for looking up specific values, it can also be useful for performing joins, okay? And as he said, if you look at PG stat indexes, you'll see how often that index is used, right? And that was a great point you made. Sometimes the index is going to be used on the replica, right? Don't just check, if you're going to remove it, check the usage count on the replica as well. Make sure both systems aren't using it before you go ahead and delete something like that, right? But again, you can see not only is an index useful for looking up individual, like where column equal 12, right, which is typical index, but even a join can use an index. And merge join also will use an index. So there's two of them will actually use indexes. Now, another smart thing is, remember I said they were all made of X's? I created like a dummy column. Well, I'm going to ask for A's. And what's really cool is that Postgres does not believe me. It's like why are you asking for X's? There's none in there. A's. There's none in there. Postgres is going to assume there's one A just for the heck of it, right? And it's going to do a nested loop with an index-only scan because it's like this is going to be so easy. It's going to be really fast. It kind of does that. Now, if I change that the A's to X's, all of a sudden a nested loop that looks really easy. Now it's like okay, now we have a lot of rows. So remember I said nested loop for small tables, small queries, but this is now a big query because there's a lot of X's there. And you can see it actually knows how many rows are going to be hit. Okay. To kind of wrap this one up, I'm going to talk about limit. How many of you have used the limit clause? Okay, limit clause actually came from MySQL. I mean, I don't know if MySQL, some people probably still use MySQL, but years ago, back in the early 2000s, I think, MySQL came up with this limit idea. We thought it was great, so we copied it real fast. We were appreciative of that idea. What limit does is effectively limit how many rows come out of a query. So this query we've seen before, no where clause, right, does a hash join. But if I do a limit 1 on it, I'm basically saying, listen, I want ordered by sample ID, I only want 1 row. Okay? So this one without the limit, back up, it's going to return all the rows. As soon as I say limit 1, it's like, oh, now it's become easy again. I'm going to do nested loop, right? Remember I said nested loop for small queries? Now it's nested loop. He's like, okay, we're gonna run through, but we're only gonna return 1 row. The limit clause actually tells the optimizer not to run the whole thing, and the optimizer uses that information to pick a better plan. So this was a really cool thing. Not only does it, you could do this with cursors. How many SQL cursors? Anybody? Yeah, one. Okay, but now limit's even better because it tells the optimizer we're only going to return 1 row, and effectively we get a nested loop here. If we ask for 10 rows, we still get a nested loop. If we ask for 100 rows, we're like, okay, now it's getting too big. We fall back to a merge join. All right. What's really weird is when we go to 1,000, it goes to a hash join, which there's some reasons for that. In a merge join, because the sides are ordered, you can kind of hop out quicker when you're going. But once you're at 1,000, it's kind of going to run the whole query and then give you your numbers. That's the way. It's going to actually hash the inside and then sort it. And then if we run vacuum, which updates the visibility map, and this is related to what Sargis talked about with index-only scans, now all of a sudden I can do an index-only scan. And we fall back to merge join again. Remember, this was hash join. Now at 1,000, we're back to merge join again. And then if we have no limit at all, we're back to merge join. This is crazy, right? So with no limit, it was hash join. Then with a limit 1 or 10, it was nested loop. Limit 100, it became back, it went to merge join. Then the limit 1,000, it went to hash join. And then when we ran vacuum again, it flipped back to merge join because it knew it could do an index-only scan. Okay? And then again back to no limit, and then when we go back to no limit again, because we've done the vacuum, we don't go back to hash join, we go back to merge join. Like, wow, this is just crazy. I mean, I remember running this, and I'm thinking, and what's weird is when I originally wrote this talk, it didn't do this. And again, as I said, these talks are updated very frequently, for pretty much every release or every 2 releases, so I actually ran it again. I'm like, hold on, something weird's going on. So I actually ran sort of some extra stuff, and this is that smart. It's happening. It's the vacuum. The vacuum is allowed an index-only scan, and effectively changed what was possible here. Okay, I'm going to have another talk beyond joins and indexes. What I've given you is the basis of the optimizer, right? Sequential, scan method, join order, and the basics. And what we're going to talk about after the break is actually all the 42 other things that the optimizer does. Because I've given you the bare bones. When we come back, we're going to talk about that. And we will on a break. Thank you again, ma'am.
Thank you.
Great. So as I said before, the first talk was the basis of the optimizer. What we're going to be talking about now, all the other things that it does. I unfortunately only have 21 minutes for this presentation, but again, we have time after for questions, and I think it's just great to get together. So again, we've seen this talk. We understand what that is about. There's a URL for the talk. Remember I mentioned 43 other things? 42 other things? There you go. Right? These are all the other things that Postgres does, and we're just going to walk through them. And they're in groupings. So for example, these are all related to aggregates. This is related to parallelism. This is related to common table expressions. And again, we'll just kind of walk through and give you an idea of the other things this optimizer is capable of doing. I also mentioned that there are configuration variables that allow you to control some of these, so you can turn them on and off in case you want to change how Postgres behaves. So let's first off, I'm going to use a special explain command to turn the cost off, just to make it simple. And here's the first one. It's just a constant. Select a constant. Return something called a result. Remember I mentioned the last time you could watch my talk? Well, there's my SQL right there. Same issue, where you can basically download the SQL and watch this talk kind of fly by. Okay? So here's a values clause. I'm not sure how many of you are aware that Postgres supports a values clause. You can do that, and you can actually generate multiple rows with a values clause. And that is how a values clause is done. By the way, you're going to see a lot of complex queries. Usually the blue is what's causing the red. So blue is the start, red is the output. Generate series in a from clause. That actually is kind of a cool feature of Postgres, and that we call that a function scan. Anyway, anytime you put a from clause, you're going to get a function scan. The gentleman asked me, you asked me, like, does this change a lot? These don't change pretty much. Like every time, well, no, yeah, there are some cases it does change because we move stuff around a lot too. But again, usually that's what's going to happen. Incremental sort, I had trouble understanding what this actually was when we implemented it. But effectively, an incremental sort is a case where you have some of the columns are sorted. Some of the early columns are sorted, some of the later columns are not. So this allows us to sort only the later columns because we know the first ones are already sorted for us. So effectively here, I've got an index on the first column, but I'm ordering it by the first two columns. And effectively, I get what's called an incremental sort. It already knows that X can come from an index, and then it just has to sort the second column. Okay. This is the way it works. Again, blue is sorted, pink is not. And again, in the output, both are sorted. Okay. Distinct, you may know Postgres supports a distinct keyword here, and that actually generates something called a unique node, we call it, which effectively just removes any duplicates from the output. Same thing with union, without the all clause. If you use union, the duplicates are removed automatically. That's just the way union works. If you say union all, you don't get the duplicates removed. But union itself, you remove duplicates, and then again, we get a unique clause there. Union all, again, as I said, union all doesn't remove duplicates, and we just append the first result to the second result. So again, be aware of that. This gets a lot of application developers. Every time you use union, distinct, or intersect, a union, except, or intersect, remember whether you want duplicates removed or not. And if you don't, you should really be using the all keyword there. Merge append. This is a case where I have an ordered result. I have a clause and another clause, and then I want to merge them together. But each individually is also ordered. So what I'm doing here is I'm sorting the first result, I'm sorting the second result, okay? And then when I merge them together, I can say which one of these two is lowest, this one. Which one of these two is lowest? Okay, this one and this one. Okay, this is the next lowest one. Okay, now this one. And you basically go and you just pick the lowest one as you walk along. So you're not having to sort this big result. You've already sorted the two pieces. You just merge append them. Remember merge join? Remember merge join had the ordering? There is some logic to this. I know it isn't always clear, but effectively the merge join would be a sorted result. Now we're appending instead of joining effectively. So instead of merge join, it's merge append. Kind of makes sense. Postgres does support the SQL standard except clause. And in the except clause, again, changed in Postgres 18, we effectively can take the results and just find out all of these results with these removed effectively. That's the way that operates. Remember, just remind you to use that all keyword and the removal of duplicates. Again, if you want more details, you may want to pull up the slides later to kind of get some ideas here. Setup, this is for intersect. So if you're doing a join of, here's an incremental sort, remember we saw that before, right? And another incremental sort, and you basically want the results in both together. That's what setup does, and effectively it sorts them, and it just figures out which ones are in both, and it returns that result there. Okay. Materialize is a case where you feel you're going to be accessing a table quite often, and we effectively materialize them in memory. So we take the contents of the table, usually a small table, and we just load it into RAM, and therefore we can access it much quicker than going to shared buffers to pull out the rows. So we materialize here because we expect that this not equal comparison is going to have to do a lot of comparisons here, right? So because we're doing a lot of comparisons, instead of having to go to shared buffers for that, we can effectively load that table into local memory and do the not equal comparisons much faster. All right. Any questions? Any questions so far? Okay, great. Memo-wise, this was introduced, I think, in Postgres 14, 15, something like that. Oh, I got a Wi-Fi network. We'll do that. I normally don't, I had trouble understanding what this did, and I thought the name was kind of odd, but effectively, it's a case where you're joining a table that has a lot of duplicates, and it's too small for a hash join. And you have another table that is too big for a hash join, and then you have an index. And effectively, what this does is you join a table with a lot of duplicates, and it memoizes them. Again, a nice URL here explaining, Postgres 14. Okay. What effectively it does is it basically, when it does a lookup on this inner side, it will create an in-memory copy of a small segment of those results. Typically, this is too big to just fit in memory, so we just create a cache, and then we just compare against that cache. We also have a negative cache that we remember, and it just allows us to do this kind of comparisons much quicker. Okay. Again, when we can't fit the whole thing in, we can't materialize it because it's too big, we create a small version in memory, okay? And we just keep that version refreshed. And that's what Memoize does. I didn't think it was that big a deal, but people were super excited about it. And it turns out that there's a lot of queries that do this kind of duplicate, tables too big kind of query. And this was a big deal for them, so that's great. Group, I didn't know you could use a group by with no aggregate, but in fact you can, kind of cool. And what group does is effectively take a bunch of rows and shrink duplicates into one row. So all these basically, let's see here, this one, oh, this looks like a line is wrong, I'm sorry. Oh no, this one goes here, this one goes here. I need a line for this one, I think, right here. So this one, this 2.5, and then, yeah. So it just basically groups them together. Here's another example where all the ones get grouped together, all the twos get grouped together, and all the threes kind of get grouped together. Okay. Count, you've probably seen that before. It generates something called an aggregate. Here's another example of an aggregate. And effectively all it does is it basically takes the first column and then it generates an aggregate, in this case the count. And kind of squishes duplicates into one output row. Okay. This thing pretty much does the same thing. Well, this is basically going to effectively create a hash aggregate. This is kind of funny, but you basically say, okay, Do I have an 8 over 8? No, I don't, okay? I have an 8 down here. Oh, I already have an 8 in there, so I don't need to put it in there again, okay? Do I have a 3? Yeah, I have a 3. Do I have a 6? I need a 6. Do I have a 3? Oh, I already got a 3. I don't need to do it again. Do I have 11? Let me add that. Like 6, I already got a 6. 8, I already got an 8. 6, I already got a 6. 11, I already got 11. 3, I already got a 3. I'm done, okay? So all it's doing is it's using a hash to just remember the unique values. And you can imagine this being tremendously efficient. Because we don't have to sort anything, we just kind of throw the values in there. And again, the optimizer knows like whether it should try this or not. I don't know. It's pretty amazing. Roll up, I'm not sure if I have used that. It's something you normally do in data warehouse. And again, it basically just allows you to sort, it kind of allows you to sort the result and generate the output in different levels of summarization. Kind of interesting. That's what mixed aggregate does. Window add, I have a separate talk here about window functions if you've ever used that. It's a really interesting talk, so I do recommend that. Window functions effectively allow you it allows you to generate aggregates, but at the same time keep the distinct rows without summarizing them the way group by does. Remember I said group by takes multiple duplicate rows to make one row? Window functions allow me to compute an aggregate without losing the distinctness of the rows I had. Okay. Again, I do recommend that talk if you're curious about how that works. Postgres does support parallelism. So again, if you're doing a sum on a large table, it actually figures out how to do that. Here, and I know this is really kind of an eye chart, but effectively we have two parallel scans. We have two workers that are scanning different parts of the table. This worker is summarizing these rows. This other worker is summarizing these other rows. We can then send that to a gather. Remember, we're doing a sum here, and we can basically take these two, add them together, and get the final result. All right. Now, not every aggregate can do that. Again, as I said before, there are some aggregates that can be parallelized. But again, for those that can, this is incredibly good. And this, I think, highlights Postgres' use as a data warehouse server. Years ago, you had to create a separate data warehouse, right? Whether it was, you have to basically, you couldn't use, historically, you couldn't use a relational system for a data warehouse. You'd have a separate data warehouse server, whether that was Teradata or Netezza or whatever that was. But in modern years, people are using their relational systems for data warehouse support, and again, Postgres is ideally suited for that. This is a great example. Plus the window functions, plus some of the other analytics roll-ups that I talked about. That's all part of our building up of basically data warehouse capabilities in Postgres. Okay. Gather merge, that's kind of an interesting one. It's basically a huge table that we're doing an order by. This is, let's see, this took a while. It's 100 million rows. And I just want, it's kind of weird. I want one row out of it. Right? I want this huge table ordered by the first column. I actually want all the rows. And in fact, and again, crazy eye chart, but we have parallel scans and then parallel sorts, okay? And now we're using the gather merge, which is similar to merge append. Remember merge append a while back? We took very similar. We just picked the lowest values and we kind of pull them together. Okay. And that's pretty much makes sense. Okay. Parallel append, again, same issue. It's very similar to, gather merge is very similar to merge append, except this is the parallel version of merge append. Parallel append here, I'm just doing union all on my two huge tables and I want to sort it. This is the weirdest slide I have in this deck, so just have to forgive me. But we're doing parallel sequential scans here. Then we're appending them together, and then we're sorting them, and then we're doing that gather merge again because they're separate. Again, data warehouse, you do this a lot. Parallel hash, parallel join. Again, I'm joining my huge table to myself. Okay, These are not great queries, but you get the idea. And what I end up doing here, and this is kind of a brain thing, I create a hash in shared memory. And I have to do that because I have multiple workers, which are separate processes, who are going to be manipulating this shared memory hash table. So I'm doing a parallel scan, and I'm actually loading them into this this shared memory hash. And then from this worker, I'm going to do lookups in parallel against my shared memory hash. So not only am I loading the shared memory hash in parallel, I'm now doing lookup joins in parallel from this outer side. Okay. Materialize, this is a keyword we use for common table expressions. And effectively, this is what we call a common table expression scan. I do have a common table expression talk here, if you're curious about that. And what we basically do is we just materialize the results of the common table expression. A more complicated example for common table expressions is with recursive. If you've ever dealt with recursive common table expressions, incredibly powerful. It basically, again, I'm going to have to ask you to look at the slide deck that I have. We're ready for this. But effectively, you just load a source, and then it kind of loops. It creates a loop in SQL, which allows you to basically loop over data, sort of like writing a program almost, where you're looping. And hopefully, you don't loop forever, right? But it allows you to walk a tree of data, a tree of parts, or a tree of relatives, and effectively expand out from that row to other rows, and then kind of accumulate those together. Effectively, this is the way it works. You usually prime it with some non-recursive expression, and then you load something called a work table, and that will generate an output, and then also it generates a work table, which then goes back in and continues around until no more rows come out. And when no more rows come out, the query's done, and you then send that result to the user. Okay. So that's the way those work, but again, recursive union, work table are common with common table expressions. If you do a function call in the from clause, in the target list, not the from clause, in the target list, remember this is select, there's no from clause here. You get something called project set. This is kind of cool. If you do a subquery in the from clause, you get, unsurprisingly, a subquery scan. Now, there are cases where we will optimize this and move it around, but this was an example it didn't move around and it stayed as a sequential subquery scan. If you do a select for update, we'll generate something called lock rows. If you do table sample, many of you may not even know Postgres does table sample, but it does. That generates something called a sample scan. This crazy thing, and I'm not even going to explain it because I don't understand it, but there's a special XML function that has its own optimizer plan for it. Foreign tables generate something called a foreign scan. If you want to look at physical rows in the heap, we actually do something called a TID scan. There's an invisible column called CTID, which allows you to access physical rows in the heap file, and that's exactly what we're doing there. This is actually how it works. Each file is made up of 8K. Each page of 8K has a header and an item pointer, and effectively this is item pointer, I guess, 0, 1, 2, or 1, 2, 3. Let me see, yeah, this is 1, 2, 3, and these are the data that goes with it. Okay. Insert generates an insert, not surprising. Update generates an update, not surprising. Delete generates a delete. If you try and run explain on a truncate, you'll get an error. Because truncate is not a planned query. It doesn't go through the optimizer. It just truncates the table. So it's a utility command. Again, just showing you can't explain all SQL commands, only the ones that go through the optimizer. If you do a merge command's been in Postgres for a number of years, generates a merge key. Something like this, the exists clause generates a semi-join. Effectively, what a semi-join is it's basically like a join, but it stops after the first inner match. right? It's not a full join, it's just saying, is there a row or more than one row? Yes or no? That's all it's doing with an exists. Say an in does the same thing, although the in is actually the same as, because they handle the nulls the same, so again, we sometimes can make an in into an exist, it's probably pretty much the same. Internally, it does the same thing. An in and exist both do a semi-join, okay? Not exists differently, generate something called an anti-join. And again, the definition of that is it stops after the first inner match, and then it negates the result. Not in, and for those who've read a lot of SQL, just be aware, not exist and not in are not the same. Not in and not exist handle nulls differently. The existence of nulls returning from a subquery in not exist does not cause a problem. It doesn't cause you to return no rows. If you use not in, if that query returns a null, you won't get any rows. Those of you, anybody get caught by that? Anybody? Ah, I got one. All right. I got caught by that when I was application failure.
It's in the book actually.
It's in the book. All right. Excellent. Good for Jimmy. Yeah, so that's an interesting thing I warn people about. This one is a left join. If you do a left join, this is kind of interesting. Because we created a unique index, this join went away. This is sort of the smart, we didn't code with some of the smarts of Postgres. It figured out that because this is an outer join, and we know that this can only have one row, it can't have any duplicates, we knew, oh, I'm sorry, which one? Small, this way it can't have any duplicates, and we know that this, even if it doesn't exist here, the rows are gonna come out, so we're just like, oh, we don't need to do a join here. Really kind of cool, okay? I didn't cover tuple store custom scan again, feel free to look at those. And that is it. We are at the 70-minute mark, so I thank you very much. Do we have time for questions, I think? I know that was kind of fast, but again, the meat of it was the first part. The meat of it is understanding the optimizer, what it does, how it makes your life easier. And then this was sort of icing on the cake to give you an idea of how we do parallelism, how we do some of the data warehouse queries, how we do things like common table expressions and so forth, kind of give you a full feeling of everything that optimizer can do. And you had a question? Yes?
Yes. More like a specification about one optimization, sec subquery optimization. So if Postgres really gets more, maybe joins are not more optimal than joins nested queries. You know that, or still joins are better.
Okay, so the question is, and I think we're back to this one. I expected this type of question actually.
Or I can rephrase it.
No, I think I got it. So let me just show you an example of what I was talking about here. Did I go over it? No, yeah. Yeah. So, where did I went this? Yeah. So this kind of thing. So, it took me a long time to get this query working properly. Like, Postgres will move around these queries like crazy. So it can sometimes take this query and put it up in here as a join. And it can sometimes take these queries and push them down. It has to do with whether any of these rows appear up here, and the statistics and all this other stuff. So again, this is a last ditch for us. We don't want to do a semi-join. We want to do a join, okay? So Postgres does move these automatically around quite a bit. And I had to be very specific to get a query that wasn't going to move around on me because every release gets a little better. So my point is that just because you write it this way, you may not get that actual output because we have a tendency to move stuff around pretty freely, yeah. Depending on the costs, depending on what columns are there, depending on if there's an order by, there's a whole bunch of things that go into it. But this is incredibly simple compared to the kind of queries that it will move around really freely. Other questions? Yes?
Can you talk about optimizer boundaries? I understand that sometimes there is query which gets subqueries or functions should kind of results, return result sets or something. And sometimes query optimizer can reorder nodes around for optimization purposes, but sometimes some queries deep inside are basically invisible.
Yep.
Until you run basically on your actual production data. So for me, I used Supabase a couple years ago. It used earlier security, and earlier security checks are happening basically outside of normal query planner, and actually give me quite a lot. Like simple queries become really unsustainable. So can you tell me when this boundary this happens?
Okay, so the question is where are the query boundaries and how Postgres can move stuff around?
Query optimizer boundary.
Query optimizer boundaries. So if you're interested in query optimizer boundaries, the best place to handle that is common table expressions. Okay, and this is, again, I'm going to recommend this talk, but effectively, normally when you do a with clause, there is a certain sense that a with clause is similar to a join, because you can basically take your subquery and kind of pop it up here, and then you can kind of join it down here with this, and we'll move, without the materialized word, we'll move stuff between those boundaries all the time. Okay? And there's really no way to prevent it. Now, you can create a function and mark that function as volatile, and then we won't optimize it away. And you can do a little bit with that, but I would really, if you want optimizer boundaries, the way to do that is to really use a with clause with the word materialize. And when you use the word materialize, it will not move this query down at all into the later parts, and you can control the exact order that it does things. And that would definitely be the direction I would go.
Okay, actually, my problem was the other way around. I actually wanted this boundary to disappear. But
Okay, so if you remove the materialized word, we will move them around like crazy.
Okay.
Yeah. In fact, I'm not going to go into this, but there was a time when materialized was the default, and we wouldn't move it, and we got a lot of complaints. So then we started moving it around, and we added the materialized word to force it not to move around.
Okay.
If that makes sense. Other questions? And we're out of time. Great. All right. Thanks, Emma. Really great being together with you.
Thank you very much. I would like to say thank you to WebFontaine Armenia for hosting us today, and to all of you for coming. We are going to have networking now with food and drinks, which is in the kitchen. Enjoy the rest of the evening. Thank you very much.